Welcome to the design of reinforced concrete structures, week 7, problem solving session. On the week 7, the lectures are going on design of compression members. There are already 3 lectures given in the main website. So I hope you all have gone through all those lectures and we will be solving some problems on design of compression members. Uh, Starting with the compression member, we can define a compression member as that member which is predominantly subject to the axial compression. In those compression members, columns are the main members which come under this. Different types. They can be a color based on inside the columns. So types where classification depends on many categories. For example, first can be on reinforcement basis. On reinforcement basis, another will be on loading basis, type of loading that is coming on the column or compression member. Another can be another classification can be made on the basis of slenderness ratio. Slenderness ratio. I will give a brief about each category, then we will start with the problem. Based on the classification based on the type of reinforcement, we can have tight columns, we can have spiral columns, and we can have composite columns. In this classification, we have three subcategories. We have tight columns, where another category is spiral columns. We have another category is this category is composite column. What happens in tight columns is that our main reinforcement in columns, there is a one reinforcement like this longitudinal bars, which are predominantly carrying the axial forces, compressive axial forces. Sorry. Like this reinforcement like this, main reinforcement like this in a column. This is concrete from the side, this is continuous like this, concrete side. In this, the main reinforcement is tied with the transverse reinforcement, which are known as stirrups. These type of columns are known as tight columns. Another type of column is same category, it's also a tight column. For example, these stirrups, if these stirrups are not discontinuous like this is an individual entity here, this is individual entity here. If it is not like this, but it is like this, it's continuous, making a spiral around the main reinforcement or longitudinal. It is making spiral around the main reinforcement like this. For example, if it's coming like from this side and that it rotates, comes like this, then come like this, and then come rotates like this, we can say that it's a spiral column. Composite column is another type of is another category here. What we have, reinforcement is in the form of structural steel sections. For example, we have the main section like the circular section or the I section. What we do in this, in addition to this main bars, for example, we have these main bars, four main bars at the four corners, uh, four main bars at the four corners, and the stirrup as well, like this, stirrup as well, like this. In addition to it, we have a section, steel section inside it. Like we can have I section like this. We can have I section like this inside it, embedded inside the main reinforcement. This is also type of column used. It's known as composite column, where there is a steel section inside the main reinforcement. This is the outer piece, concrete. On the basis of loadings, we have also several types of columns. We can have columns with axial loading. We can have columns with axial and loading, uniaxial and eccentric loading, and we can have columns with biaxial eccentric loading. What I mean by that is, for example, if we have this column section, if the column section is like this, sorry, for example, if the column section is like this, and we are having its axis like this, if the axial load is exactly acting at this point, that is for the centroid of the column section, like this. This is from the top face of the column, or in the from the side which we can see, we show it like this. For example, this is the top side face of the column. This is continuous from this side. The load P is exactly acting at the centroid of the section P. It's neither here nor here nor here. It's exactly at the center. We can say that it's a column with axial loading. Another type, this is column with axial loading. You can see that this is a column with axial loading. Another type is loading with uniaxial eccentricity. There is axial loading on the column, but it is having uniaxial eccentricity. That is, with respect to one axis, it is having some eccentricity, and with respect to other axis, it is along that axis. For example, like this, we have same column section. Same column section. This is a column section, and this is the axis of our column section, like this. If our load is centric with respect to this axis, but it is having some eccentricity with respect to this axis. For example, if it's acting at like this point, or load P is acting at this point, it means that it is having some eccentricity E with respect to this axis, like this. It means that, for example, if it is dimension D side is it's D. Now on the side profile we can show it like this, how this load is acting. Can show, for example, this is the central line of the column. If it is not, if this load would have been acting along this line, we would have called it as action loading. But it's not acting along this line. It's acting somewhere else at some eccentricity along this E P along this. It's acting along this with some eccentricity. We can call it as loading with uniaxial eccentricity because with respect only one axis. Loading with uniaxial eccentricity. Eccentricity. Another type is with, if this load eccentricity is with respect to both axes, then we will call it as loading with biaxial eccentricity. In that case, our load will be acting like this. For example, this is our column section. This is our column section, and if this is our axis, like this is one, and this is another one. Our load might be acting like somewhere here. It is having some eccentricity like this one. It is having some eccentricity like this one also. You can call it as ex. It is having some eccentricity ey here, for example. This is xx or y axis. Same column with biaxial eccentricity. Loading with biaxial eccentricity. Another classification is based on this one, slenderness ratio. Slenderness ratio. Slenderness. Slenderness ratio. Actually, slenderness ratio is a geometrical property of a compression member which is related to the ratio of the effective length to its lateral dimension. The ratio is called slenderness. It provides actually the measure of the vulnerability to the geometric failure, because we know that our column may fail buckling. Buckling is a geometrical instability which comes in our column section. If our slenderness ratio is very large, because it's effective length divided by lateral dimension. Length divided by lateral dimension. Lateral dimension. If it's very large, slenderness ratio is very, it means that its effective length large and lateral dimension is very small. It means that it will have large length like this. It will have large length like this, and its cross section will be small. Sorry. Large length like this, and its cross section will be small. This one will be small. In comparison to another column, it will have slenderness ratio less. And compare the slenderness ratio of these two. it is slenderness ratio S1, it is having S2. S1 will be greater than S2 because we are looking at here its effective length is than this one, and here its later dimension this one. Dimension we have to take here. Please do check. Is here it is greater, it's lesser, it's inversely proportional, so clearly S1 will be greater than S2. And also we can say that clearly that if the loading on the both columns here P1 P2, we can say that it will columns buckle at less load as compared to this one. And it depends on the material as well, but giving that material is also same. That's why slenderness ratio plays an important role while designing our column. So we have to make sure that we are designing a column with respect to appropriate slenderness ratio. Because we have to first categorize our column this on this slenderness ratio, whether we are doing it in a short column or we are designing it a long column. And long column is also known as slender column. By this terminology, you can understand why slender column, because it's having large slenderness ratio as compared to the short column. So there is provision in code given that uh, 25.2 says that a composition member can be classified as short column if its slenderness ratio with respect to major principal axis as well as minor principal axis both are less than 12. For example, we have this column section like this. Like this, we have coordinate system like this, x, y, if it is dx dimension, if it is dy dimension, this column is having effective length lex in x direction and ley in y direction. You would have studied these concepts in the online lectures given there, why lex and ley may be different in the different cases. This is the effective length in the x direction and y direction. There is a detailed calculation of the effective length of the column. Lex and ley puts both slenderness ratios, that is lex dx, this will slenderness ratio x direction is x, and ley by dy is equal to sy, that is sx is less than 12 and sy is less than 12. If both the slenderness ratios in both the directions are less than 12, then we should design this column can be categorized as a short column. And if this is not the case, short column. If it's not the case, that is Sx greater than 12, any one of the two, Sx greater than 12 and Sy, if both are greater than 12 or any one of the two is greater than 12, Sx greater than 12, we can categorize this column as slender column. Slender column or long column. Okay. So this is the classification given by the code based on the slenderness ratio of the column, and this is one of the main important factors for the designing of our column. But this slenderness ratio is measure of the buckling, whether the column buckle or not. So we will straightly to our design problem. What we have to do today. Another one concept is here minimum eccentricity. Minimum eccentricity. Code says that while designing the column, we have to check for the minimum eccentricity. What it says that if the eccentricity of the loading that we are applying on our column, Ex minimum, we will be given from the analysis part. The loads would have been already calculated. That, for example, X kilonewton loading is happening on our compression member. Now they are giving to the designer that for this X kilonewton loading, and this X kilonewton loading is acting at some eccentricity on our my column section. The designer design the column section, design the reinforcement for this column section. So the main eccentricity in both the directions, Ex minimum and Ex minimum. Yeah, code says that first calculate the minimum eccentricity Ex minimum. How will you calculate that? Code has given the empirical formulas for that. Ex minimum is equal to L by 500 plus dx by 30 or 20 mm, whichever is greater. We have to take greater values. Greater one. And we have to EY minimum. L by 500, it will be same like that. L by 500. Here L is the unsupported length. Plus here it will be the lateral dimension along y direction, dy by 30. And same 20 mm. Greater one. When you have the actual load acting on your section, you will select and you are giving the unsupported length. That is the you are giving the constraint that, for example, your floor length should be 2 meter or 3 meter. Is the constraint given. What happens after that? You will check the code formulas for minimum eccentricity of x and y direction. L for L for x direction is this, and for y direction it's this. Now you will compare this minimum eccentricity with the eccentricity of the loading that's acting on the column. If the eccentricity is less than the minimum eccentricity, then it will be designed at this column as a column with actual loading. If it is not, then we will have to go to the other design procedures where we have to design the column with maybe uniaxial eccentricity or biaxial eccentricity. If it is greater than if its eccentricity is greater than minimum eccentricity along only one direction, it will be uniaxial eccentricity. If it is greater than if its eccentricity is greater than both minimum eccentricity, then we will have to design it loading with biaxial eccentricity. That will be in the further lectures of this series. So this is the main check that we have to perform while designing our column section. Minimum eccentricity. So our problem is design problem is we have to design a reinforcement of a column for size of 450 mm by 600 mm, and this column is subject to the actual load of 2000 kilonewton under this service load, both dead and live load. What the given for this column is having an unsupported length of 3 meter, and it's braced in against in both directions. And for use moderate exposure that we can have M20 fabricate, and we can use Fe415 steel. So our column section is like this. We are given like this column section, or in column section, and it said that we are given a column section like this. It's having one dimension. This one is 100 mm. Another layer dimension is 40 mm. Will be writing every dimension in mm, so no need of writing the units. 450 mm, and it's having imported length. Li will be denoting as unsupported length of 3 meters. 3 meters is for the 3000 mm. 3000 mm. And we have to use M20 and Fe415. Fe415 complete. I think so. Fe415. So we have this data given. We have the steps for proceed for the design problem. So we will first step is whether it is short column or slender column. Short, yeah, or slender. Which is whether the short column or slender column. We can do it by slenderness ratio. So we have unsupported length given as Lx in x direction is given as both in y direction is given as 3000 mm. 3000 mm, and we are given as dy as 450 mm, and dx as 600 mm. The coding exercise 600 mm. So slenderness ratio S will be equal to, for both directions, it will be effective length Lex divided by d scatter dimension in x direction dx. It will be Ley effective length in y direction divided by dy. Ley dy. It will be equal to kx divided by Lx divided by dx. Ky Ly by dy. Here the fact to the supported length converts unsupported length to the effective length. Usually this factor k is having different values depending upon the conditions. So we can write both these as, because in our problem and conditions were not given. Let's keep these for time being kx and k values as unknown. Later we will see kx times 3000 divided by 600, because dx is 600. What is it? It is 5kx. And same in this, it will be ky times 3000 divided by 450. What is it? It is approximately 6.6 ky. So in both the cases we have seen that it is 5kx and 5kx. Now in the question it was given that the column is braced again sideways in both directions. Effective length ratio kx and ky are both less than unity, hence the two slenderness ratio will be both less than 12. Like this one. It is column is cannot like this sides it cannot move. So we can have both the slenderness ratios because kx and ky will not exceed more than 1. So we can have both slenderness ratios sx, sy less than 12, because its value can roughly be equal to 5 point something, or this will be 7, or maybe it will be up to 7, but these two values will never cross 12. So both slenderness ratios are less than 12, so we can design our column as short column. Short column. Column can be designed as a short column. Now the next step is minimum eccentricity. He wrote the formula for the action. X minimum is equal to 3000 divided by 500 L by 500 plus Ax by 30 is the formula. Ax is 600 divided by 30. How much it comes? It comes out to be 26.0 mm. Where it was given as either this or 20 mm, or and we have to take the greater of the two. It is greater than 20 mm, so we will stick to 26 mm as the minimum eccentricity. In 50 by 30. So calculating this value, it comes out to be 21.0 mm. And it is greater than 20 mm, so we will stick to this value. So the minimum eccentricity comes out to be this one. As per the code, the eccentricity that we have to take is, so 5% we have to take. 5% will be 0.05. We will have to check the 5% of both these little dimensions. 5% is 0.05 of dx, and we have to check 5% of dy as well, 0.05 dy as an eccentricity acting for the to be designed it as a actually loaded column. When we check both these values, this comes out to be 22.5 and 2.5 this is also greater than Ax minimum. It's all greater than E1. So as per this code check, we can design this column as actually loaded short column. Like that, it's actually loaded short column. An actually loaded short column. The third step is to calculate the loading factor. Loading is also given, but we have to calculate the factored load acting on our short column. Factored load. The factored load is the service load coming on our column was given as 2000 kilonewton. So multiplying its partial load factor, we will have PU. Factored load as load times partial load factor. Partial load. Our load is coming as 2000. Per load factor we will take as 1.5. As per code, we will have 3000 kilonewton PU. So now for the design of the longitudinal reinforcement, point. First we will design of longitudinal reinforcement. So we will use the formula given by the code for axially loaded short columns as PU ultimate load is equal to 0.4 FCK AG. AG is the gross area of cross section of the column. AG 0.67 FY minus 0.4 FCK ASC. This formula discussed in detail in the lectures available on the central portal. It's actually simply as the load carried. This is the load carried by our concrete that is present in the our column section, and this is the load carried out by or shared by reinforcement. Or here you can see that the stress coming in our reinforcement. This time is ASC, area of the compression reinforcement. So when we plug all the values, we know PU, FCK, AG, FY, FCK, and ASC. We will ASC is only unknown here. So plugging all the values here, PU is 3000 kilonewton. We have 3000 10 power 3 Newton. We have 0.4 FCK. We will use 20. We have A gross as 450 times 600. 600 plus we have 0.67 Fy. We were given as 415 minus we have 0.4 FCK is 20 and ASC is only unknown. That's the area of the compression reinforcement. When we solve this for ASC, it comes out to be ASC 3111 millimeters. 3111 millimeters square. So we have to distribute this ASC in longitudinal reinforcement, and we have to keep in the mind the sections of the column as well. Since our column is longer in one direction and shorter in another direction, we will first assemble this area such that we will place first 4 longitudinal bars at 4 corners, and then we will arrange another remaining area in the other columns, that we have to put the bars at the intermediate between the 2 corner bars. First we will use, let's provide let's go with this trial. Provide 4 25 mm diameter bars at corners. Let's go with this trial. If we check this as these are 4 and 4 25 mm bars, we will have pi by 4 25 square. If we calculate this, pi by 4 25 square, it comes out to be 1964 square. And let's provide also 4 additional 25 bars at the intermediate, at the midpoints of the sides. Additional. This is the minimum requirement, because for the rectangular columns we have to minimum place 4 bars at the 4 corners. 4 into pi by 4 into 20 square. Let's calculate this value. This comes out to be 1256 mm square. If we sum it up, this comes out to be ASC provided comes out to be 3220. Clearly you can see that it is greater than ASC required. So we will check this for minimum reinforcement requirement as well. provided percentage of the reinforcement that we provided is 3220 divided by ag gross area is 450 times 600. Once again, minimum reinforcement of 0.8%. It's 0.8%. It's as per the code. It's greater than 0.8, so we will minimum reinforcement requirement is okay. Minimum reinforcement okay. This requirement is passed. So now we will arrange these four bars at four 8 bars that we provided in different locations. Before that, let's check for the lateral ties. Lateral ties that we will provide for this longitudinal reinforcement. Lateral ties as per the code tie diameter. This tie diameter, that's phi of t, should be greater than any of the following. We have to check for this. It is phi longitudinal, the divided by 4 bar, maximum diameter of the long bar divided by the 4 or 6 mm. Any is 25 by 4. This comes with greater than 6. This greater than 6. So let's go with the diameter and tie spacing. As per code, we have to provide as tie spacing. ST will be less than any one of the following. It is either least lateral dimension. It's either least lateral dimension or is 16 times minimum reinforcement, diameter or longitudinal reinforcement that we provided, or 300 mm. Any of the two. Let's calculate 16 times minimum we provided 20 mm. It is 320, and least lateral dimension is 450. Least because another one is 600 mm and this is 300 mm. We have to provide the minimum of the all three, so we will provide 300 mm. Here we provided 8 mm. So we provided, therefore we provide 8 5 ties, 8 mm diameter ties at the rate 300 center to center. 300 center to center. The center to center spacing is actually from the centroid or lateral tie, from one lateral tie to the another lateral tie. That's why we write it center to center. This is this one. So let's show it in a sketch how we designed it out. It's like this. First we have column section like this. This was this here and there. So we designed our reinforcement like this. This one we provided. First we provided like this. We will have uniform cover from all the sides. Okay, we will have longitudinal bars at 4 corners, 25 bars. 25 5 bars actually. This is main bar 1 here. This is another main bar here. This is another main bar here, showing with one color. This is one main bar here. So the color coding here is, this is 25 pi longitudinal bar. Another we have 20 mm. We will show a different color. We provided at intermediate points, midpoints of the between two. These are of smaller diameter. Provided here, and we provided it here. So this we provided as 25 longitudinal bar. Okay. We will, for this mid bars, we will have another staggered. We will have, which will another. We will have another step here. This. We will have this continuous here. This is continuous here. This is continuous here. Continuous here. Actually, for these steps, like and for this step, we will have like this. Okay, so reinforcement details are complete, so we will write our dimensions. It's like this. This was given as 600 mm. This was given as, this was given as 450 mm. 450 mm, and what we provided, this provided by corners we provided there and 425 at middle of each face. At middle of each face, and we provided these as, we provided these as 8 times at the 300 center to center, and these are staggered. So this completes our, and we also provide clear color. I forgot to mention. Clear cover 2 times 40 mm. This is the minimum. So this completes our the reinforcement detail and the type, and this is a complete design. So proceeding in the same manner, you can solve any problem related to the axial loaded column. You will be given unsupported and load acting on the column. From that point to decide whether it's a short or a long column. Then we have to decide whether the eccentricity on the column lies within the minimum eccentricity. If it is in minimum level, we can design it as actually loaded column. Then you have to proceed with finding all the reinforcement materials. Thank you everyone for joining today's session. Thank you. This session is over.
Thank you.